Hi, welcome to another lecture for Psych 671. So this one should be a little bit shorter. So this is wrapping up our discussion about interactions. Okay, so today we're going to talk about interactions between categorical variables. So just to kind of cut to the chase, usually when you just have categorical variables, you just do an ANOVA. So if you took Psych 607 or if you've taken another stats course that focuses on things like ANOVA with categorical variables, you're probably kind of already familiar with this. So what I'm going to do first is I'm going to go through how you would do this in regression. I'm going to go through it kind of quickly because you probably won't be using this method very much. And then at the end, I actually added some new slides just today to incorporate an R example so we can kind of really compare the results from a traditional ANOVA to the results of a regression and then see kind of what we would need to do to in R, say with regression, to get the same output for an ANOVA that we typically get in like SPSS or JASP or a program like that. Okay, so what if we want to look at the interaction between two categorical predictors? This model would be set up similar in form to how it's set up when we have one categorical and one continuous variable. We would dummy code each categorical predictor. We can also use other coding, so this will come in at the end when I talk about how to get the same output from ANOVA. So dummy codes have the advantage of being familiar. They also have the advantage of if we want to compare different groups, so just to see, is this group different than the other? Normally if we were doing ANOVA, we would do that with like post hoc tests or something, but with regression, you typically just compare contrast. So regression might give you a little bit more power than post hoc tests if you're interested in just comparing groups, because it doesn't correct for multiple comparisons. So that's just not something within the regression framework. So that's one difference. But for now, we'll first show how you would do this with dummy coding, and then at the end we'll use contrast coding. That's more similar to what SPSS does when it does a regression and then spits everything back out in ANOVA format. Okay, so we make the products of the dummy codes to enter the interaction. So after we dummy code the predictors. So each predictor again needs G minus 1 dummy codes. We can call the predictors A and B and their number of levels, little a and little b. Okay, so predictor A needs A minus 1 dummy code, and then predictor B needs B minus 1 dummy codes, and then every possible pair of dummy codes from the two sets is multiplied to make up the interaction. So they're going to be A minus 1 times B minus 1 interaction terms. Okay, so there's also, A minus 1 times B minus 1 degrees of freedom from ANOVA. So there are three groups of predictors that have to be kept together as sets. So the A minus 1 dummy codes for predictor A, the B minus 1 dummy codes from predictor B, and then the interaction terms have to be entered as sets. Okay, so each set can be added to or removed from the model only all together. So the rule of including lower order terms also applies. If the interaction terms are included, then we need both sets of dummy codes. They also have to be included. Okay, so each set is then tested using an f-test of r-squared change. So this gives us like partial effects for predictor A, partial effects for predictor B, and then the interaction effect partialing for the lower order effects as well. Okay, so say we're studying the effectiveness of three different antidepressants. We expect their effectiveness to vary across women and men. So these are two variables we're treating as categorical. Okay, so our predictors for antidepressant, we're just using kind of old school SSRIs. I don't know what the current medicine is for depression, but Prozac, Zoloft, and Paxil have been around for quite some time, and I guess they're still being prescribed. I really don't know. So there's Prozac, there's some Zoloft, and there's some Paxil. And then for sex, we have female and male. Okay, and so the outcome variable is just some depression scale. So, different scale that we use for depression. So for sex, let's make women the reference group, since maybe depression is a little bit more prevalent among women than men. I think that's the case, but don't hold me to that. And so we would dummy code females as 0, males as 1. And then for antidepressants, let's make Prozac the reference group because it's the old standard. So obviously this isn't a scientific classification, but maybe Prozac has been around a little bit longer, or it's more prevalent. So we say that we're going to make it the reference group. And then we need 2 dummy codes for antidepressants. So A1, if that participant took Zoloft, they get 1. If they took Paxil, they get a 1 on A2. Okay, so we can label the dummy codes based on the names of the variables they represent to make it easier to keep them straight. So I've labeled it S1 for sex, and then A1 and A2 for antidepressant. Okay, so we also need to make the product terms by multiplying all the possible combinations of the dummy codes for the 2 variables. So we have S1A1 and then S1A2. Okay, so we just have 2 product terms, in other words. And then we can set up our regression equation. So here it is right here. So we can figure out what the regression equation is for each possible combination of the categories. So doing this will clarify what exactly our coefficients mean. So this is just like what we did when we rearranged to find simple regressions for continuous by continuous predictor interactions. So because both predictors are categorical, the results are going to tell us, will all tell us differences between means of combinations for different means, but for different combinations of conditions. Okay, so basically we can look at different means. We're going to have 3 levels of antidepressants, 2 levels of sex. So when we factorially combine them, we're going to have a total of 6 levels. So then men, we'll have people taking Zoloft, people taking Paxil, people taking Prozac, and then the same 3 levels for women as well. So there are coefficients right there. So for women taking Prozac, S1, so the dummy code for sex equals 0 because they're the reference group. And then Prozac is the reference group, so both A1 and A2 equals 0. So let's plug in zeros for those dummy codes right there. And then the model just reduces to B0. Okay, so B0 from this model gives us the predicted depression level for a woman taking Prozac. For a woman taking Zoloft, S1 equals 0, A1 equals 1, A2 equals 0. We plug those values in, and so we get Y predicted, depression score predicted in this case, equals B0 plus B2. And then for women taking Paxil, same thing, but now we plug in a 1 for A2 and a 0 for A1. Okay, and so that reduces to B0 plus B3. So those coefficients added together get us our predicted depression score for a woman taking Paxil. Okay, and then for men, we kind of do the same thing. It gets a little bit more complicated because we need more interaction terms. For men taking Prozac, now S1 sex equals 1, but then A1 and A2, the 2 antidepressant codes, equals 0. So we plug those values in. We get Y equals B0 plus B1. So that gives us the predicted value for a man taking Prozac on depression. And then for men taking Zoloft, we plug in 1 for S1 and then 1 for A1, 0 for A2. Okay, so plug those in, and so we see we got now an interaction term we're actually using over here. So this was S1 and A1, they both equal 1, so 1 times 1 is 1. So now the combination of these 4 coefficients give us the predicted depression score for a man taking Zoloft. And then for a man taking Paxil, we do the same thing, except now A2 equals 1 and A1 equals 0. We plug those 1s into the regression equation, and then it reduces to these 4 coefficients. Okay, so, you know, a combination of 4 coefficients, but this is different here. So B3 plus B5. So adding all these coefficients up, remember these could be positive or negative, so you know some of them could kind of cancel out, and that gives us the predicted depression score for a man taking Paxil. Okay, so you know it's pretty simple and straightforward. You get these combinations and they just equal like the predicted expected values or mean values for that group. Okay, so Y predicted equals B naught. Y predicted for women taking Zoloft equals B naught plus B2. For women taking Paxil, B naught plus B3. For men taking Prozac, B naught plus B1. For men taking Zoloft, B naught plus B1 plus B2 plus B4. And then for men taking Paxil, B naught plus B1 plus B3 plus B5. Okay, so B naught is the mean in the reference group on both factors. B2, so we have that right here, the difference between the means for women taking Zoloft versus women taking Prozac. B3 is the difference between the means for women taking Paxil and women taking Prozac. And then B1 is the difference between the means for men taking Prozac and women taking Prozac. And then B4 is the difference between the simple difference between Zoloft and Prozac for men versus women. And then B5 is the difference between the simple difference between Paxil and Prozac for men versus women. Okay, so B1 captures the simple effect of sex within Prozac. B2 and B3 capture the simple effect of antidepressant within just women. Okay, so those right there. So that's just the dummy code for antidepressant. But it's for when the reference group equals 0 or the other predictors equal 0, and so that's for the reference group of women. And then B4 and B5 capture the interaction or the difference in simple effects, the effect of sex within antidepressant. So say for each antidepressant, you know, is there a difference between Prozac and how that affects depression levels for women versus men? Within Zoloft, is there a difference between depression for women versus men, and then within Paxil? Or we could do the effect of antidepressant within each level of sex. So for women, is there a difference in the mean depression scores for women who take Prozac, Zoloft, or Paxil? And then for men, is there a difference in the depression scores for men who take these 3 different drugs? Okay, so here are our results right here. So R squared equals 0.056 for the whole model. That's significantly different from 0, albeit, you know, kind of barely. So not a whole lot, not a huge effect, but 5.6% of the variance explained. Okay, so here's R squared change for adding sex. So that's significantly different from 0. Okay, and then R squared change for antidepressant is not significantly different from 0. Okay, so within women there wasn't a significant effect of antidepressant. And then R squared change for the interaction is significantly different from 0. Okay, so that accounts for an additional 4% of the variance. Okay, so here are our coefficients right here. So we've worked out the interpretations of the coefficients so we can calculate the means for each combination of categorical variable values. So in other words, we can take these coefficients right here. We know that the intercept equals the predicted depression score for the reference group for both variables. So that would be for women taking Prozac. So their predicted depression score is 19.3. Okay, we know that sex is the simple effect within at the reference group for antidepressants, so within Prozac for men versus women. So we know that for men, they score a little bit lower on depression when taking Prozac. Okay, so we'll interpret these other effects in just a minute. Okay, so there's our coefficient B naught. Okay, and then for Zoloft, for women taking Zoloft, we take that coefficient and then we add B2. So if we go back and look, B2, the coefficient, so this is B1, this is B2 right here. it's negative, so negative 2.231, so that equals 17.03. And then for Paxil, we subtract coefficient B3, and we get a predicted depression score of 17.6. And then for men, we take the intercept and then subtract the B1 coefficient for sex. And so that gives us the predicted depression score for men taking Prozac. For men taking Zoloft, we add in the B2 and B4 coefficients. We get a predicted score of 17.85. Okay, and then for men taking Paxil, we get predicted score of 17.24. Now all of these, if you just computed the means for each group, all of these should come out to about the same thing, or I think they should come out to exactly the same thing as the means for each group. Okay, so if we're trying to think of like where the interaction might be between, it might be kind of that for men, you know, it looks like Prozac leads to like lower depression than the other two, Zoloft and Paxil. Whereas for women, we have 19 versus 17 and 17.6. So for women, Prozac led to higher levels of depression. So, you know, we might conclude, this is made up data, but we might conclude that if we were looking at this, maybe Prozac works a little bit better in men than in women, assuming depression means is positively scaled. So like higher values mean more depressive symptoms. So if that was the case, then that's probably the locus of our interaction right there. So the interaction is significant. Our R-squared change equals 0.040, P equals 0.018. So we need to look at the simple slopes. So because both predictors are categorical, the simple slopes are all just differences between means for one predictor within the levels of the other. So simple slopes here are exactly the same as simple effects tests in ANOVA. Okay, so B1 tests the simple effect of sex within Prozac, the reference group. Okay, so if we look at the predictor, we labeled it S1 for sex. So that estimate for the coefficient is negative 3.675, and our p-value is 0.01. So that's a significant difference there within Prozac. Okay, B2 and B3 together test the simple effect of antidepressant within female. So within the reference group. Okay, we look at that. It looks like a p-value of 0.114, so there's not a significant effect of depression or antidepressant within females. So then we only could get two simple effects tests there with this dummy coding. So the effect of sex on depression within Prozac, the effect of antidepressant on depression within female. To get the test of all the simple effects, we'll have to make up new dummy codes with different reference groups and then rerun the regression. Okay, so recall that we had to do this to get particular tests of differences between means, even when there was only one categorical predictor. So there are our original dummy codes. Okay, sex and antidepressant, Prozac and females were the reference groups. Okay, so t-test of B1 tests the simple effect of sex within Prozac. Okay, and then the f-test of R-squared change for B2 and B3 tests the simple effect of antidepressants within women. Okay, so new dummy codes for sex, we code males as the reference group now. And then for antidepressants, we just leave it the same. Okay, so now the t-test of B1 would give us the simple effect of sex within Prozac. Okay, I think that's what we just got. Yeah, so we just got that above. Okay, but now the f-test of R-squared change for B2 and B3 tests the simple effect of antidepressant within men. So up here we did that simple effects test within women. Now we would do the f-test of R-squared change, and it would be testing that simple effect of antidepressant within men. Okay, so new dummy codes for antidepressant. Now let's make Zoloft the reference group. Okay, so t-test of B1 tests the simple effect of sex within Zoloft. So we haven't done that yet. Okay, the f-test of R-squared change for B2 and B3 tests the simple effect of antidepressant within women. Okay, we could have new dummy codes for antidepressants. So now let's label Paxil as the reference group. Okay, so t-test of B1 tests the simple effect of sex within Paxil, and then the f-test of R-squared change for B2 and B3 tests the simple effect of antidepressant within women. So note that both of these right here, we basically already got those simple effects tests. Okay, so the only new thing that the dummy code has gotten us in this case are these t-tests of B1 testing the simple effects within Zoloft and then within Paxil. Okay, so by making these new dummy codes of different reference groups, we can get the tests of all possible simple effects. We'll also get many duplicate tests. Of course, we should only report one of the two sets of tests of simple effects, so sex predicting depression within each level of antidepressant, so within Paxil, within Prozac, within Zoloft, and then antidepressant predicting depression within each level of sex. So is there an effect of antidepressant within women? Is there an effect within men? So this is just like what we do with continuous by continuous interactions in regression, and it's also what we do when we report simple effects in ANOVA. Okay, so we didn't go through all those, so I'm not going to belabor this too much because you'll probably be doing ANOVAs usually, but that's what you would do, is run all those with those new dummy codes basically. And so what if the interaction is not significant? If it's not significant, then it suggests the effects are additive. So we could interpret the results in one of two ways. We could ignore the presence of the interaction and interpret the simple effects as main effects. So it's like first order effects applying across the levels of the other predictor. Or what's more commonly done, at least in regression, is we drop the interaction terms, we rerun the regression, and interpret it as ordinary multiple regression. Okay. So note that these results with interaction terms give us simple effects within levels of the other predictors, or partialed for any other predictors, not main effects of predictors. So ANOVA with two predictors is going to give us interaction terms and a main effect. So it'll have one interaction effect and then two main effects. Then we can examine simple effects. Okay, so regression can handle models with higher order interactions. We just need to dummy code all the predictors, create all possible interaction terms. So for example, for a model with 3 dichotomous predictors and all interactions, our factors would be A, B, and C. And then the dummy codes for factors are A, B, and C. So we label them conveniently. So this would be our model right here. So A is the dummy code for factor A, B for factor B, and then C for factor C. Okay, and then we have the 3 two-way interactions and then the 3-way interaction right there. Okay, so yeah, it might be a little confusing notation. So regression would also allow us to add continuous predictors to the model. So going back to our original model, so we had sex and antidepressants. Okay, we could say have that same model, but maybe we want to add 2 other continuous predictors, okay, as covariates. So all categorical effects are now partialed for continuous predictors x1 and x2. So this is basically what we do when we do ANOVA. So if we take a step back, we can use regression procedures, SPSS regression. We could do regressions in JASP. We could do in R, which we'll get to in a minute, to test models with categorical predictors and their interactions. We can fiddle with the coefficients to figure out the group means. And we could remake dummy codes and rerun the model to test all the simple effects that we would test, say, with simple effects tests in ANOVA. Okay, but you might be asking yourself, and I asked the question as well, isn't all this kind of an unnecessary headache? So there's a picture of someone experiencing a headache. Okay, so interactions between categorical predictors, at least this is an opinion, are more easily understood in the framework of ANOVA. Okay, so ANOVA procedures like SPSS's GLM will do the coding for us using the by command. It'll hide the coefficients. Maybe we don't care about them. I don't know. I've kind of started to care about them a little bit, but it'll hide them regardless of whether we care about them. It'll show the f-test of r² change that we do care about. Okay, and then it'll show the means so we don't have to work them out. And then it helps us easily do comparisons between means using post hoc tests and test simple effects. Although, of course, a lot of people, including me, are a little bit skeptical or critical of post hoc tests and maybe the ANOVA framework in general. Okay, so when should we use the ANOVA framework and when should we use the more general regression framework? Well, I think this is pretty common advice. So use ANOVA when all predictors are categorical. So like when it's, say, an experiment with experimental groups. Use ANCOVA when any continuous predictors are used as controls and are not themselves of interest. Use regression if there's at least one theoretically interesting continuous predictor. So this is a lot of times usually when we'd be interested in looking at an interaction between a categorical and continuous predictor. Or when we're interested in looking at the effects of this other continuous predictor as well as the effects of the categorical predictors. Of course, these are just my rules of thumb. I think they're pretty common, but they're just opinions, so you can feel free to violate them. They're not hard statistical rules. Okay, so let's look into this just a little bit further, this relationship between regression and ANOVA. So we'll do an R example. So in both this course and the previous ones, like 607, I've talked about how ANOVA is just a special case of regression, or a special case of the general linear model. So what does SPSS or JASP do when they perform ANOVAs? Okay, so R by default uses dummy coding, whereas SPSS uses effects or contrast coding to make the interaction and main effects orthogonal to each other. And then SPSS and JASP also by default use Type III sum of squares for ANOVA, whereas R defaults to Type I. So I'm not going to get into the differences between Type 1, 2, and 3 sum of squares. There's a lot that's been written on them. I think, my philosophy as well, Type 3 is pretty good. It's fine. So if SPSS and JASP have been using them, then Type 3 is probably the most common in our field of psychology. So how can we get the results to look kind of similar if we do it in R versus JASP or SPSS? So let's look at an example of a two-way ANOVA that we did in Psych 607 from some of my own published data. So these data are from Worthy, Otto, and Maddox, 2012, in Journal of Experimental Psychology, Learning, Memory, and Cognition. So one factor was working memory load. So people either performed a decision-making task while also performing a working memory demanding dual task, or they performed under single task conditions. So dual task manipulations are pretty common for inducing like a working memory load. Basically what participants had to do is they saw two numbers, they had to remember the size and actual value of the number, and then they performed a decision-making trial, so they had to maintain that information about the numbers they saw first in working memory, and then after performing each decision-making trial, they're asked, okay, was the number on the right or left larger in size, it's like font size, or numerical value? And so they had to keep information in mind. It taxes working memory, and the idea is that might affect decision-making processes or working memory processes needed to perform the decision-making task. So the other factor, in addition to working memory load, was task type. So in one task, choosing an option that led to smaller immediate rewards but larger future rewards was optimal. So we're going to call this the future optimal task. And then in the other task, choosing the immediately rewarding option was optimal. So we're going to call this the immediate optimal task. Okay, so dual task people were predicted to do worse in the future optimal task, but better in the immediate optimal task because they couldn't learn the future effects of their choices. So we found that, and it was a really strong effect, and we replicated it as well. If I had to put kind of one study where I'd bet a lot of money that it would replicate, I think this would be probably my number one choice, because the working memory load manipulation is really powerful, particularly under the future optimal, for the future optimal task. Okay, so I've created a new R script. So open up the categorical by categorical interaction.R script. Okay, and so you can see that it looks like it does down here. So change line 1, I guess this is actually line 2. So I added in a line where I based this on a similar example right here and gave the link if you want to see it. It's pretty short, and there are also some other examples I looked at as well. So there you can kind of Google R Helmert contrast type 3 sum of squares ANOVA to kind of find out more about what exactly is going on here. So change line 1 to where your Psych 671 RStats folder is located. So this is just like what we've done in the other R script. So you could open another one that you've modified this line in first and then just copy it and paste it here. Okay, so you'll probably need to run lines 4 and 7. We're going to use two packages called CAR. I think it stands for something like applied regression, I forget. So it doesn't have anything to do with the automobile, but an interesting name. And then the SJ stats package, that's going to give us some effect size statistics that we'll use in a little bit. So you'll probably need to run line 4. And I think it says, do you want to install the source, the package from the sources, and you have to click yes, so go ahead and click yes. And then after you've done that, run line 5. Okay, or actually you can run lines 4 and 7, install them, and then after that I would go ahead and comment out line 4 and line 7 by using a pound or hashtag, hashtag sign. Used to be the pound sign, now it's changed into the hashtag sign. And so comment those out and then run lines 1 through 12, so that'll load these libraries that we're going to use, and then it'll load the data right here. So if you're in the working directory and the data file, it should be in your RStats folder. I think it is, but I'll send it just in case. But it's going to look in that current directory based on this / right here. And then it's going to pull up the data set, and then it's going to show the first 6 rows. So we see for working memory we have single task, then below I think it's labeled dual task. We'll look more into the levels in a minute. And then for task type it's listed right here, and then optimal choices is our dependent variable. So there are more variables. I think it's broken down by different blocks, but these are the only variables we're going to use for this regression and ANOVA that we'll do. So the factors working memory and task type are what we'll use to predict optimal choices. So run line 15. So we wrote these in strings, or the data are in strings or text format. So like, it says future optimal written out rather than saying like 1 for one condition, 2 for the other, or something like that. So they're called string variables rather than numeric variables. Okay, so since they are, R is going to order the factors alphabetically. So this gives us the levels, and so we see that it's calling dual task before single task. Okay, so if we're using dummy coding, this is actually something really good to know about using R. So if we're using dummy coding, R is going to automatically make the first level listed the reference group. So it's nice because it makes the dummy codes for us, And say if we wanted to just reset the reference group as a different group, we could just change the orders of the levels, which is what we're going to do in lines 18 and 25 down here. So maybe we want single task to be the reference group. So dual task, D starts before S. And so it's going to be the reference group because it's listed first alphabetically. So if we want to reorder that, we can run lines 18 and 19. Okay, so this tells R to recompute the working memory factor by reordering the levels. So the level that was second now becomes as the first one listed, and the level that is first, dual task, now becomes the second one listed. Okay, so now when I run line 19, it shows me the levels are single task and then dual task. So in other words, it's listed first. Single task is going to be coded as the reference group, and dual task is the comparison group. Now run line 22. So we can see that future optimal is first, and then immediate optimal because F comes before I. So let's reorder that. Most decision-making tasks probably would be like immediate optimal, where you're just trying to maximize immediate reward rather than having any of this kind of delay discounting effect in. So we'll use that as the reference group. So if you run lines 25 and 26, this reverses the order to where immediate optimal is the reference group. So what we're doing at the end of lines 18 and 25 is just telling R to make the second factor the first and the first factor the second. Now, if you had 3 or 4 levels, you would do the same thing in form. So there would be, if you say you had 4 levels, you would write out 1, 2, 3, 4 in any order, and then that would specify like what order you want them listed in. So if you are using dummy coding and you want to just recode them real quick in R, you can just rearrange the order of the levels using similar syntax to this right here, and then check that they're in that order, and then you can see that the first one listed is going to be the reference group, and then it's going to make dummy codes for the ones, the groups listed after that. Okay, so I think that's something really general, and it can really save you a lot of time over making all these dummy codes in Excel or something like that. R will make them automatically for you. So yeah, like I was saying, we won't be using dummy coding here, but this code could be very useful if you want to manually set the orders of the factors. So if you wanted to rerun the regressions with different groups as a reference group, you just reorder the level so the reference group is listed first. Okay, and then R's linear model command will then make the dummy codes for you, and then run the linear model command with those dummy codes. And then this also applies if you use the BRMS package. The BRM command will work the same way. Okay, and the LME4 command will as well. So LMER will, or GLMER. So now let's go to JASP. So this is a r/JASP example, I guess. Let's use JASP to run an ANOVA, and then we can compare it to what we get in R using regression. So open up this data set in JASP. So within JASP, find it within the Psych 671 RStats folder. And after you have it open, click on ANOVA, and then ANOVA again. Okay, and then enter optimal choices as the dependent variable and task type and working memory as the fixed factors. And then you should see the ANOVA output right here. So we have a significant interaction, okay, and then we also have a significant effect of task type, no main effect of working memory. Okay. So now back in R, let's run lines 30 and 31. Okay, so line 30 and 31, this is just going to set up the default way R sets up contrast. So you probably won't even have to run these lines. I had to run them because down below I reset them as something else, and so then I had to reset them as the defaults. So treatment right here refers to dummy code. So this is like if we're treating one group as the reference group and other groups as treatments, it gives us coefficients that represent like differences between the reference group, the control group, and then each treatment group. So now let's run lines 34 and 35. So this is our model with an interaction term. So we got model 1 equals linear model, optimal choices, regressed on task type by working memory. Okay, so again, the star, the asterisk, it tells R to run the interaction model with all lower order effects. Okay, and then we're saying our data is data 1. And then this print summary M1, I said to print it to 6 significant digits. That's to help give us enough digits to where we can compare the output to the output from JASP using ANOVA. Okay, so here is the output for R. So this is what these are the coefficients right here. Okay, so we got the task type future optimal. So this is specifying what group is being compared to the reference group. So we set immediate optimal as a reference group. So this is comparing the difference between immediate optimal versus future optimal. And then this is the dual task. So it's saying dual task is the comparison group compared to single task. Okay. And then here is our interaction term specified by the colon. Okay, so the t-value for our interaction is negative 4.26, so if we round. Okay, so I had it print out to 6 significant digits, so we have plenty to look at here. So go ahead and run line 37. Okay, so this line I just typed out, I think negative 4.25968 squared. And then that comes out to 18.144. So if we look down here, this matches the F value for the interaction from JASP ANOVA. So for the interaction effect, R gives us the same F value, that is equal to T squared. Okay, and then the same P value as well. Okay, so, but if we look at the p-value for task type, so it's significant from the ANOVA, but if we look up here, it's definitely not significant. Okay, so that's because it's just giving us the simple effect of task type within the reference group for working memory, which is single task. Okay, so for the single task condition, there is basically no difference in performance between the two tasks. Okay, so it's just describing the simple effects of task type within the reference group. Okay, if we look at the t-value, so negative 0.53709, so that squared, that's certainly not going to equal about 25. So 5 squared equals 25. This is nowhere near 5. So this is definitely different than the output that we're getting down here for the ANOVA. Okay, so now let's run lines 46 through 47. So this changes the way R is computing contrast from dummy coding to Helmert contrast coding. So contrast coding makes the main effects orthogonal to each other and orthogonal to the interaction effects. Okay, so orthogonal means that they're not kind of correlated together. They're testing each effect individually. So this is a way of coding the data so that the interaction effect is not affected or doesn't affect the lower order main effects. So now run lines 49 through 50. So if we look back here, lines 49 through 50, so now we're running the same model. We're calling it M2. The only thing we've done differently is changing the way R is computing contrasts. Okay, so we run that same model, lines 49 through 50. Now we still get the significant interaction. It's the same effect. That didn't change anything, but these lower order effects change. So now there's a significant effect of task type. The t-value is negative 5.01. Okay, if we square that value, it looks like it's probably going to match or come pretty close to this f value. So t squared looks like it's going to be equal to f. We run line 52 to check that. Okay, and indeed we get 25.111, and that's the same exact value we get for the f value. Okay, so it matches the f value for task type. Okay, we could also look at this t value for working memory. So negative 0.01524. I think I did that. Already. So let's look at that. So what was it again? So negative 0.15024. So we have to put this in parentheses actually, 0.15024. And then we square that. And so that equals negative 0.0223. Okay, negative, or not negative, but 0.0223. Okay, and so that is not significant, and we get the same p-value as well. Okay, so we can see that everything lines up, in other words. Okay, so now run lines 55 through 56. So this uses the ANOVA function from the car package. So the capitalization is important. There are some different functions. There's an AOV function that I think defaults to running type 1 sum of squares. But then this ANOVA allows you to specify the type. Okay, so we specify the type we want, which is type 3, which is the type that SPSS and JASP give by default. So a lot of people, I've read stuff about people trying to switch to R, and they notice that the ANOVA results aren't right, or they aren't correct. It's not that they're incorrect. The highest order coefficients are still the same, and the overall model will still be the same. But it's that the contrast coding is different, so it's specifying the main effects as different, as simple effects rather than as main effects. Okay, so now when we do the ANOVA, we just take the ANOVA. So if we look at lines, where do we have 55 and 56? So if we look at this right here, okay, so we run the ANOVA right here. Okay, and so we get that output, and then this actually gives us the, takes the model that we ran, the linear model, and then puts it in ANOVA format. So everything is the same, just that t squared equals f in the original format, but this just gives us the code and the same output that we'd get from ANOVA. So we can see how different things line up. So the sum of squares, 1.216 was 0.001, and then 0.878. So everything lines up. The f values are the same, and the p values are the same. So now we have identical f and p values as the ANOVA from JASP. So this really shows kind of what is going on and what SPSS is doing when it runs everything as a regression and then spits it back out in a ANOVA format. It does that by running a type 3 sum of squares that uses Helmert contrast coding. Okay, and then you can see that it notes in JASP down here, this is a type 3 sum of squares. Okay, so you could also run lines 58 through 65. So these are from the SJ stats package, and they give effect sizes. So if I look at lines 58 through 65, okay, so right here, okay, so these basically take the ANOVA output and then compute eta squared, partial eta squared, so same, and then partial equals true, and then omega squared. Okay, so coming back to this, yeah. Okay, so go back to JASP, and then under additional options, scroll down to display, and check estimates of effect size, and then all three options. So I'll give you a minute to do that. So these in other words, we're getting the same effect size estimates in R that we would get in JASP. Okay, so here are our JASP results. So we can look at eta squared, 0.183, 0.132, partial eta squared, 0.211, 0.162, and then omega squared, I guess in JASP this is negative in R, but maybe in JASP it just is bounded at 0, but 0.174, 0.124. Okay, because effect sizes are proportions, so they can't actually be 0. Okay, but everything lines up very nicely. So now we've done kind of come full circle. We've done everything in R that we would do in JASP basically, or SPSS. Okay, so now I would recommend go ahead and running lines 68 through 69. This will reset R's default method for coding contrast to dummy coding. I don't know if it would default back automatically when R restarts. It might, I'm not sure. Or stay as Helmert contrast, but I think it's probably a good idea to reset it. This is a global option, so you expect R to dummy code unless you tell it otherwise. Okay, so hopefully this kind of shows and makes everything kind of come full circle from what we're doing when we do ANOVA to what we're doing when we do regression. We've now, talked about most of the things dealing with regression that are analogous to ANOVA. So in the last few lectures, we just have a couple of other topics. So we'll talk about mediation, and then logistic regression, and then multi-level modeling. So hopefully this has been informative, and we'll pick up there next time. All right, thank you.